Okay, so we're recording. Let's see here. Last time, here's where we left off. We were talking about the very, very, very beginning of section 1.2. And starting off to talk about parameterizations. Again, quick reminder, y'all should have seen a lot of Chapter 1 material in your linear algebra class, 218, 221, whatever you took. So I'm, again, picking and choosing how we spend the very limited class time we have. So parameterizations is something I don't expect that you've seen. So we are going to spend a bunch of time talking about parameterizations. So the big idea, position is a function of, I'm going to say time. You don't have to, I mean, technically it doesn't have to be time, right? But it's a nice little physically satisfying, geometrically satisfying little crutch to think of it. Because with this point of view, where you think of position as a function of time, then a parameterization basically draws the curve. Right? If you have x and y giving you where you are as a function of when, it literally kind of traces out the curve. Okay, so here's an example. Let's look at this one right here. Here's a parameterization. Notice that position, x and y, right? X and y tells you, oh, whoops, I knew that was going to happen. Position is x and y tells you where you are, and notice that it is a function of time. Right? Okay, so specifically, x is this function of time, and y is that function of time. So now one thing you could do, I don't really particularly recommend this, but you could, I suppose, use this formula for x as a function of time and like have your finger kind of do what it says, right? And then you could take this formula for y as a function of time and have your other finger do what, and then you could kind of try to do like this and then follow it's very confusing, right? That's not at all what I recommend. Much easier to try different things, and a great idea is to try to find a relationship between the given x and y and then see what you can determine from that. So for example, here we have that x being cosine t and y being sine t. Notice that x and y satisfy this convenient familiar relationship, and we just kind of got lucky and happened to be that we know a convenient relationship between sine and cosine. Right? We didn't derive this relationship, we're just noticing and then taking advantage of it. Right? So what this tells us is that every point that is created by this parameterization, in other words, as you draw, every point that you sort of touch as you move, always satisfies this equation and therefore is always on this circle. Right? So that's our very, very strong tip-off that what this is a parameterization of the unit circle. Right? So it's a clever little move. So again, sometimes you get lucky and you can just notice a relationship between x and y. Now, you might not be so lucky. Here's another example. Here is a parameterization. Parametric curve. Position as a function of time. Again, notice. Right? So how would I figure out what this is? And there's different ways to do this. First, let me remind you again what this all means. Let's see here. This is x. Don't forget that's x. That's when you have a parametric curve. The first coordinate is telling you what the x coordinate is, and then this is y. Second coordinate of the curve. Position, that second coordinate position's typically y. Okay, so the big idea here, and again, every example is different, but in this case, what works really nicely is to take this equation and solve for t, right? Then take this other equation and take that formula for t that you just found and plug that formula for t into where that other t is. Because after all, it's the same t. Right? So you solve for t in one equation, plug it into the other equation. And then you just kind of move things around and notice that your equation turns into that, which you can simplify to that. And life is good. You look at this resulting equation, and again, a very familiar equation. We know what that is. It's equation of a line. High school algebra. No problem. Everybody on board? Okay, so now is this how you do it? So I want to point out, a reminder, this is a class about ideas, not a class about algorithms or answers or things like that. What we have here is an idea. This is an approach that works sometimes. It doesn't work every single time, right? Notice this particular method of solving for t in the first equation kind of hinges on actually being able to solve for t. What if this was some wacky formula, some transcendental expression that where you literally cannot solve for t? This method stinks, right? So what you have here is one method that works sometimes. And my favorite metaphor for this is to think of this as one of many tools in your toolbox. Screwdrivers are great for certain purposes. They're terrible for other purposes. Screwdrivers are no good at all at putting nails into a board. They just don't work, right? So think of this as, again, just one tool of many, tool for your toolbox. It is nice to have a toolbox full of tools. You pick out the tool appropriate to your situation. Okay, here is another tool, totally different approach that we could take for how to find the relationship that helps me understand what this parametric curve is. Let's take the formula for x. Let's see, I'm going to try to get my colors right. Here's the formula for x. And let's look at the formula for y. And what I'm going to try to do is first, just qualitatively, I'm going to ask myself, do these look related, similar in any way? Do they seem to have anything in common? And, well, they're totally different formulas, but they are both constant times t plus another constant. They actually have a lot in common, right? And in fact, I can imagine a process by which I would take this expression and do stuff to it and make it turn literally into this expression, right? And if you just do that and just keep track of what you've done, out comes the equation you're looking for. So in particular, we start with our formula for x, arbitrarily, doesn't matter. Here's our formula for y, right? And I just kind of ask the question, well, what do I have to do to the expression for x to turn it into the expression for y? And now let's just look and see what I did here. Well, obviously, this t minus 1, I would have to multiply it by 3, because I see that I'm going to need a 3 down here. And then my constant at the end is all wrong, right? It's a minus 3. I need it to be a plus 4, so I add 7 to both sides. Notice I'm keeping track on the left of what I'm doing to the x expression in order to turn it into the y expression. And the resulting punchline, as desired, is that I have a relationship between x and y. Notice it's the same relationship that I got above. So two different methods, useful in different circumstances. The first one, arguably very handy, but it requires being able to solve for t. Notice this doesn't require that. This second method, though, kind of requires being able to see a way clear, right, some sort of a path that will allow you to turn this expression into that expression. That may or may not be clear. In this case, both work. We got lucky. But two different tools, use them appropriately. Pausing. Questions? How are we doing? Everybody's happy. Okay. What if you have a three-dimensional parametric curve? And I say this is a three-dimensional parametric curve because notice it, the location, which is a function of t, that location, it has three coordinates. Okay? So this is what we call a parametric curve in R3, or sometimes people say a curve in space. Okay? Okay, an equation is not going to answer the question for us. If you have an equation in space, an equation of three variables, you would expect to get a surface. We know this is not a surface. This is a curve. So an equation's just not going to cut it. So we're going to have to take a different approach here. Again, tool for your toolbox. This won't work every time. The neat observation I'm going to make is that if you ignore z, if you look just at the x and y coordinates, familiar. Right? Now that's I'm going to call that a little bit of wishful thinking. Wouldn't it be nice if we didn't have to worry about that z? Wouldn't that be great? So how can I turn that wishful thinking into something meaningful? What does this tell us about our actual curve that we face? And I'll point out the act of ignoring z is something geometric. It's a projection into the xy plane. It's like I'm taking whatever point I'm looking at and just shoving it down into the xy plane and thinking of it only there. Is that cool? So, in fact, when I do this projection into the xy plane, in other words, when I ignore the z coordinate, in other words, when I look at this familiar looking expression here, what I'm doing is I'm looking at the shadow down in the xy plane. Right? So, cool, I already know this one, cosine t, sine t, that's a circle. Sweet, that means that my shadow, whatever this curve is, my shadow down here in the xy plane is a circle. Everybody on board with that? Okay, now, what else do I notice? What else is convenient? And I notice this z, pretty easy little formula. I understand that very well, right? T just means as t increases, that expression, t increases. Simple as that, right? So what does that tell me? Well, of course, looking at only the z-coordinate, ignoring x and y, is a what you might call a projection into the z-axis. It's just kind of throwing all the horizontal component away and just sort of smushing everything onto the z-axis. So, said differently then, knowing this simple formula here for z is telling me that the projection to the z-axis, in other words, if I kind of smush it together, in other words, if I only keep track of the height, then the height is doing what this says. In other words, the height is just increasing at a constant rate. So what we have now is two partial pieces of information about our curve. I know what the projection looks like down into the xy plane. I know what the height is doing. And now if you kind of put them together, right, so the xy coordinate is doing this, right, the z coordinate is doing that, and now just use your three-dimensional imagination, that's going to make what we call a helix. So all together then, let's see if I can, something kind of like that. Now, look, this is very ad hoc. This is how this particular one happens to work out. Again, tool for your toolbox. This idea of looking at projections won't always just magically give you the answer, like it worked out pretty conveniently in this case. But sometimes this is super handy. Okay. Everybody all right? Yep.
Why would it make like a cylinder? Like when it's being projected, why does it swirl instead of going like this?
Yeah, because there's only one t is the short answer. And whatever t you plug in, it's the same t describing where you are in the circle that also dictates where you are height-wise. Right, so when you're at a certain height, if you look at at a certain height like that, right, there is exactly one value of t that gets you to that height, which means that there is exactly one value of t that you plug into the x and y, which means there will be exactly one, I'll say point in the projection down here, which therefore gives you exactly 1 point at that height. Does that make sense? So as you're going up, you don't get a full circle of points as you go up. You only get 1 point on the circle as you go up. Is that satisfying? Mm-hmm. Okay. Yeah, cool. All righty. Oops. There we Okay, so moving along. So what we have looked at here, let's see if I can get through that. Hopefully that'll stay. What we have looked at here is given a parameterization, given the formula for position as a function of time, how do I figure out geometrically what it looks like? So let's take it the other direction. What if I know geometrically what it looks like, but I want to find the parameterization? I want to find the formula that gives position as a function of time. So if you know what the curve is and you want to create the parameterization, this is called parametrizing the curve. And there are, again, various different methods. I have a kind of I'm going to call it a personal favorite in the sense that this is the one that works the most often in some reasonable sense. And it's also super easy, which I love, of course, also. And this is a method I like to call the graph parameterization because it works specifically for graphs. And we'll see some extensions later. But the big idea is if you have a graph, in other words, if you have one of the variables written as literally as a function of the other, not that this will always be the case, right? Some curves don't do that. But if you can write one of the variables as a function of the other, here's the simple trick that makes it all just kind of work. Just let your parameter be your input variable. It's as simple as that. Everything will just fall into place kind of automatically. Let your parameter t be the input variable. So in this case, I would let my parameter t be x. Now let's see how that plays out. Here's an example. So here's a curve that I want to parameterize. I know what this is. It's a parabola, right? Old news, high school algebra, etc. How would I create a parameterization for this? Notice first, this is a graph. I have one of the variables written literally as a function of the others. Well, there's only one other. So, okay, great. I'm going to let that input variable be my parameter t. And then it's all over. I've basically already won. It's just a matter of putting the pieces together. So if y is equal to x squared and x is equal to t, well then that sort of forces y to be t squared. And lo and behold, I have position as a function of t as required. So easy. Everybody see how that worked? Okay. All right, so please, please, please make sure to know this very simple rule. Again, if you want to use this trick, again, condition, it's got to be a graph. Right? But assuming you have a graph, just let t be the input variable, and it always works out. Now, here's another example. This one's a little bit less of a freebie. Here's a nasty-looking equation. Pretty scary. Ooh. What does this curve even look like? I have to admit, I don't know. Off the top of my head, this is hard, right? I could probably figure it out if you gave me a little bit of time and pencil and paper and let me kind of play with it. But good news, you don't even have to know what the curve looks like as long as it's a graph. Now, it's not currently written as a graph. I don't currently have one of the variables solved for as a function of the others, but I could. Right? I can just solve for x, in this case, as a function of the other variable, as a function of y. Now, very importantly here, x is the only variable you can solve for. If you try to solve for y, you're in trouble. Right? It's not going to work out. So don't try to solve for y. Nothing magic about y. Right? You solve for either in terms of the other. It's totally fine. Here I'm going to solve for x because it's easy. I then let... let's see here. Blue. I then let t be my input variable. My input variable is y, so let t be that input variable. And then if y is t And if x is this function of y, then that means x kind of has to be this great big expression of t right there. And again, victory. Sure enough, we have position as a function of just t. All right. Neat one. Love it. All right, again, not every tool works for every scenario. Here's one where the graph parameterization will crash and burn badly. This curve that I'm going to give you is a weird curve. The idea of this curve is that I have a wheel, and you could imagine a wheel rolling along the ground. I'm going to let the x-axis be the ground here, just arbitrarily. Imagine this wheel were to take off and start rolling to the right. And then imagine that there is I like to think of this as a bicycle wheel reflector. And I don't know if y'all have seen this phenomenon, but if there's a bicycle going down the street and there's a reflector on the outside rim of the wheel, that reflector makes this kind of choppy, jumpy curve about like that, right? So that's my curve, right? How do I parameterize the path made by the reflector? And if you try to solve for y as a function of x, you're going to find that that's not a friendly process. Okay, so what we're going to do is use a totally different method. The big idea is that wherever that reflector is, even though the path followed by the reflector is hard, I can think of this very conveniently as a sum of simpler things. And in particular here, I'm going to talk about the axle. There's the axle. I'm going to call it A, the axle of the wheel. Right? The axle is actually doing something really simple. The axle's just going in a straight line. That's easy. Okay. Now, that's not what I'm interested in, though. But let me point out further, there's also this, I'm going to call this the D vector. This is a vector that goes from the axle to the reflector. And I claim that that is actually doing something easy. Now, it doesn't at a glance look like it. At a quick glance, you're going to look at this picture and think, oh, yeah, that arrow is doing some weird thing. But it's not. Because this thing, what I have in red, what I'm calling D here, not an arrow. This is a vector. Vectors have a direction and a magnitude. They do not have a location. Right? I can take this red arrow, I can redraw it anywhere I want. It's the same vector. Vectors are just direction and magnitude. They completely could not care less where you put it. And so let me do this so I can get it all visible. I still need to. Okay. So that red vector, what I'm calling D, I can think of with its tail at the origin. It's free. Right? Put it wherever I want. Kind of easier to have it be with its tail at the origin. And at that point, what this red vector is doing is actually also pretty easy. That red vector is just going around in a circle. Nothing to it. Does that make sense to everybody? So this is the powerful observation here. Using vector algebra, I can think of this extremely scary, intimidating-looking curve of the reflector as a sum of two much simpler things. The axle's straight line. This red vector D, circle. So now we got a couple of details to work out, right? But the big picture strategy is already kind of revealed itself that if you want to understand the reflector, understand first the axle and that D vector. Okay, so now the details. How do we actually, get this done? Take them one at a time. Let's start with the axle. Let's see here. My axle, again, is right here. Let's talk about let's start with the y-coordinate of the axle, just because it's a freebie. Very convenient. Notice that the y-coordinate is always A. This is a straight horizontal line, so as the axle moves along, the y-coordinate never changes. So let's just write that down. Got one in the win column, right? Nothing to it. Okay, now let's talk about the x-coordinate. What is the x-coordinate here? The x-coordinate, I see from the picture, that x-coordinate is this distance. And the way I'm going to interpret that for the purposes of what we're doing here, that distance is, that's the amount of road that has touched rubber. As of this moment, this particular moment that we're interested in, the rubber was touching the road here, and then as it rolled over to here. So only this road has touched rubber. And then now here's the important physical observation, and this is just the way bicycles work. This is the way wheels work in general. The amount of road that has touched rubber must equal to the amount of rubber that has touched road. And that's physical, kind of empirical. You just have to kind of think that through. That's right. That's just how that works. I hope that makes sense to everybody. Is that satisfying? Physically satisfying? Road equals rubber. Okay, so if I want to know, as I do, I want to know this x-coordinate, that means that I want to know this distance. That means I want to know how much road has touched rubber. Well, that's equal to the amount of rubber that has touched road. And so the x-coordinate that I'm looking for, what I really need to compute is that distance. And this is an arc of a circle, and we have formulas for arc of a circle. And in particular, you notice that I'm using t, this angle, as my parameter. And a pretty easy formula for how to write, the length of an arc of a circle in terms of that, the corresponding angle. It's just radius times angle. Radius, of course, is a, and that means that my x-coordinate is a times t. All right, everybody on board? Okay, now here's a detail I've left out. Why did I use t as being this angle? In other words, t, what's going to be my parameter for this parameter? Why did I choose that angle? It's kind of arbitrary. Oh, question, yeah.
I have a question. So t
yeah.
here isn't time because your t would cycle through, right?
Yeah, no, t is going to increase. It doesn't go back to zero once you've made it. Angles can be arbitrarily large, right? So t is going to increase arbitrarily. That said, you're right. It's not really time in this case because it's an angle. I can't assume I don't know anything about how fast this wheel is moving, right? So it's a little of a stretch to call it time, but it doesn't. You don't have to.
It measures progress in terms of angles, then.
Yeah, that's right. That's right. But I'm going to continue to think of this as kind of behaving analogous to time. It's something that's increasing as the process progresses. In some sense, time doesn't really matter here because we're just interested in the shape of the curve. We're not actually interested in how fast the wheel's rolling. Is that cool? Yeah. Okay. All right. Okay, so why did I choose this angle to be t? I'm going to say convenience, and what I mean by that is this angle t. You'll notice it starts at 0, right? Where the reflector is when we first start this process is where that angle t is 0, and then furthermore, as the wheel rolls, that angle is increasing. So it's geometrically convenient. It behaves in this algebraically convenient way. It starts at 0 and increases. Seems like an easy choice. Okay. All righty. So, okay, right. Whenever you do a parameterization, you do have to choose what your parameter is going to be. You want to think strategically about what's going to fit in conveniently with the geometry of the problem that you're actually working. So it'll be different in every question, right? So try to make it something that's going to be geometrically convenient and something that behaves in a reasonably natural, satisfying kind of way, such as in this case. Okay. Okay, so let's talk about the d vector. Again, sort of going around in a circle. There's my d vector. The don't forget, here's my parameter t, like that. And good news, if I want to know the location of this vector, in other words, if I want to know that point, make sure you remember the sort of the duality, the sort of the equivalence, the correspondence between points and vectors, right? And tail at the origin, etc. So you can think of this as being an arrow, or you can think of it as being a point, and coordinate-wise, same thing. So where is that point? And I remember high school trig class, and we talk about this angle over here called theta, right? Everybody remembers that's typically how we write theta. And given that angle theta, it's just, yeah, sure, the coordinates for d, no problem. It's radius times cosine theta, radius times sine theta. High school trig. Sadly, though, not written in terms of t. I need position as a function of t. So I'm going to have to find a relationship then between t and theta. And that's the good news. In this case, this relationship between t and theta is they always add up to 3 pi over 2. And again, this is a matter of looking at the picture. As t increases, in other words, as this thing rotates as it does, as it rotates to the right, t keeps getting bigger, theta keeps getting smaller. Okay, whatever, but the total is always 3/4 of a term, aka 3 pi over 2. And where did I? Here it is. You can then take this formula for theta, plug it into there, and simplify using your angle addition formulas, and you get this for your d vector. Oh, wrong color, of course. Sorry, the d vector. Right there. Now again, this is just how the particular details happen to work out in this particular circumstance. Every example is different. It's not always going to go down exactly like this, but you can see kind of some of the ideas that I used here and adapt appropriately to different circumstances. Okay. Oh, and real quick, I do want to make sure that everyone knows the angle addition formulas. I'm going to write this down. This is important. I'm going to say this is really a requirement for the course. Cosine and sine angle addition formulas. Man, what in the world? Make sure you know those. A lot of high school trig classes, they sort of mention them and say, you don't need to memorize it, but honestly, it comes up a lot in multivariable calculus, and frankly, any kind of analysis, anytime you're dealing with vectors and real world and applications, they come up a lot. So I do think everyone should know them. And I'm aware that high school classes let you slide on that, but now that you're at Duke, I need you to know them. So just cosine and sine. Don't worry about like cosec and stuff like that. Just sine and cosine. Okay, everybody all right?
Can you go back over how you got the relationship between theta and t?
Yeah, so the observation there is that between the two of them, they give you, I wanted to be the highlighter mode, they give you a 3/4 turn. Okay. So that's all it is. Yeah. Okay. Alrighty, so moving along, next example, suppose we have a line. We want to parameterize a line here. We know how to write equations for the line. There's a temptation to say, if you know how to write the equation, then aren't we good? We've got an algebraic description. Isn't that good enough? Sadly, no. When we get into chapters 6 and 7, we're going to find that having parameterizations specifically is going to be really, really valuable, really important. in order to be able to do certain kinds of calculations, certain kinds of objects that we're going to need to define. So knowing how to do an equation is not going to be good enough for our purposes. So here's the big idea. If you know something about this line, specifically if you know a point on the line, and if you know a vector, what's going on here? Oh, my stylus has already died, man. Sorry. I've got to open up the little back of this so I can get it charging, but I don't have enough fingernails to get the little thing open. There we go. Okay. Let me just get this plugged in. I'll use the other stylus here. Okay, so if about the line you know a point on the line, any point doesn't matter, and if you know a vector parallel to the line. 1 point on, 1 vector parallel. It turns out this is all you need to be able to parameterize. Now again, all I need when I say parameterization is I need to be able to write a formula for position on the line, right? As I trace out the line, I need position to be a function of t. I need to be able to write a formula for this point down here, and I need it to depend on t. And so here's the good news. There's really nothing to it. I can view that point as being my starting point x naught plus then a multiple, you'll see here, a multiple of our v vector. Right, and then let's think about what happens if I write this expression down, x naught plus tv. Well, let's see. Okay, so we start off with t equals 0. X naught plus 0 is here. As t grows, t times v always points in the v direction and gets longer and longer, farther and farther in that direction. So as t grows, you are just dragged along the line. Again, that then literally traces out the line. So, as required, we have, as needed, we have position x as a function of t. So again, kind of a neat little trick. This is a I'm going to say a pat process. You should make sure to remember this one. Just memorize this little trick. Point on the line, vector parallel to the line, x naught plus tv always works. Okay. All right. Okay. Here's another one. Oh. Here's another one. Sometimes what you want to parameterize is very similar to something you've already parameterized. So, for example, we would like here to parameterize this ellipse with this certain equation. Y'all remember all your high school algebra? Well, come on. High school algebra. They called it Algebra 2 when I was in school. I'm sure it's called something different now. So the equation of an ellipse looks something like that. And that's not, very importantly, not the same as this circle, the unit circle there, but the unit circle is something I already know how to parameterize. So I know how to parameterize the circle. I want to parameterize the ellipse. And here's where we're going to use some convenient geometric knowledge that we already have. Another fact from high school, hope you all remember, is that ellipses are what you get when you stretch a circle correspondingly. Right? In other words, if you just take the points that are on the circle and just multiply the x coordinates appropriately, multiply the y coordinates by a factor appropriately, and stretching out a circle like so will make an ellipse. So with this idea, notice what I need to do here is I need to take my x coordinates, and apparently I need to stretch them by a factor of 3. So I need to multiply by 3 in the x direction, and that's actually really easy to do. So that 3 right there, multiplying 3 times the x coordinate from my existing circle, does the appropriate x stretching for me. Notice as well, now of course this is in both directions. Notice as well, I also need to stretch in the y direction by a factor of 2. So I just need to multiply the y coordinates by 2. Thus, this 2 right there. Boom, we're done. Right? We took our existing parameterization of the circle, cosine and sine. We inferred from our, again, existing geometric knowledge about ellipses that I just need to stretch by certain factors in the x and y directions, then you do it, and then boom, there's your parameterization of your ellipse. And for satisfaction purposes, and this is exercise for y'all to do at your leisure, if you take this parameterization and if you plug that into this equation, you'll find that it works. Yes?
Would interchanging the x and y, like the cosine and sine, be like the same thing whenever you use that equation for the circle?
You said interchanging?
Yeah.
It makes you go the other direction. In this case, it's okay. But so you could switch these, and that will be an alternative parameterization for the circle. But if you switch, of course, down here, then that's going to be a problem, right? So just always make sure to think it through. But there is a version of that. That's fine. Yeah. Okay. All right. Okay. So now I want to take a kind of a step back from algebra for a moment and talk just a big picture about how to think about parameterizations and equations. Parameterizations and equations do have something very important in common. They're both algebra that we write down to describe curves. That's true. They do have that in common, but they do so in very different ways. And it's very important to make a conscious, fully aware assessment of how they are different, how they describe curves in these different ways. So very importantly, parameterizations generate points. You give me a value of t, you plug into a parameterization, out comes a point on the curve. That's kind of a beautiful thing. It's pretty neato. It's one of the reasons that we really like parameterizations, or that we will later on in the course, is that I can plug in any value of t I want, and every single time what comes out is a point on the curve. Gotta love it. Very importantly, that is not what equations do. You don't plug an arbitrary value of t into your equation for a curve. You just don't. That's just not what it is. It's a fundamentally different way of relating algebra to geometry. An equation tests points. If you have an equation and somebody says, hey, I got this point here, is this point on the curve? Well, you take that point, you plug it in the equation, and either it works, in which case, yes, it is on the curve, or it doesn't, in which case, no, it's not on the curve. Right? So, very important difference. Parameterizations generate points. Equations test points. Okay, so that's something to keep in mind. You want to make sure you know what the algebra means that you've written down, and this is an important part of that. I find that this is exactly what we need to make sense out of this example here. I want to find what points on this parametric curve are also on a plane that has a given equation. All right, so I've got two geometric objects, and I want to know which points are on both the curve and the plane. All right, so conveniently, as it turns out, we're going to find that this is convenient. That is, we have a parameterization of one and an equation of the other. So I have a point tester and a point generator. And the way that I'm going to find the points that are on both is I'm going to generate points and then test them, which I have. I have the ability to generate points, and I have the ability to test. So how do we generate points? Well, here is our point generator. Now I'm going to generate points the way point generators generate points, right? T, any value of t that I feel like I can plug into my parameterization. This is exactly what this parameterization tells me. X, Y, and Z are these formulas, and all of these are points on the curve. And then I'm going to say, hey, cool, look at this. I have a point tester. So let's take these points that I just generated and let's test them by taking those points, plugging in to my equation, aka my point tester, right? And out comes this equation, which of course is just a couple of simplifications away from this equation right here. Now let's think about what we've produced. What does this all mean? Erase this. What does it mean to look at this equation, t squared minus 1 equals 0? Well, what this says is whichever values of t that satisfy this equation, those values of t generated points that are on the plane. In other words, those values of t generate the points that I'm looking for, right? So solve this equation. Let's see here, let me get rid of that. You solve this equation, pretty easy to do, right? T is plus or minus 1. These, of course, are not points. These are the values of t, though, that generate the points that I'm actually interested in. So to finish up this question, what you would do is take these values of t, plug into your point generator, out comes your x, y, and z. Everybody all right? Cool. Yeah?
Could you speak more to like what that would mean geometrically? Like if this curve cuts the plane twice?
Yeah, that's right. That's right. The good news here is that even though it is pretty hard to draw this parametric curve, I don't really have to. I mean, the curve, yeah, it does some weird, I don't know. I think it's probably parabolic. It looks kind of parabolic, right? But I don't need to really understand that, right? That's what I'm going to call unnecessary difficulty, right? But yeah, this curve goes in some curved path, and I believe what we're seeing here is that, yes, that punches through this plane twice. Yeah, exactly. All right. Okay. So let's see here. Last thing real quick. This is pretty easy, pretty straightforward. Sometimes you have a point generator, aka a parameterization. And what you want is a point tester. And a point generator, very importantly, is not a point tester. So the question comes up, how do I convert a parameterization into what, you're going to be tempted to call it an equation, but something that plays the role of an equation at least. How do I test points? And beautiful little observation here. We're going to start off with a smart alecky ridiculous comment that if I want to test a point, well, there needs to exist. I got ahead of myself. I need to explain the math notation here, math slang. This says there exists, or there is. And this little weirdo symbol right here means so that or such that. Mathematicians find that they use these phrases super duper often, and it's just very handy to have a little convenient shorthand. So anyway, that's just terminology. Okay, so that said, if I want to test, how would I decide if a given point is on the curve? There would need to exist a value of t such that my generator generates it. Now, again, I consider that a kind of a smart alecky comment. It's not immediately helpful. That's the whole problem, is I don't know how to decide if there is such a value of t. Okay, but this works out really great as follows, because this algebra that has to be satisfied, I can rewrite. I can solve for this t in each one of the 3 coordinate equations represented in this vector equation, right? Keep in mind, when you have a vector equation, that's actually 3 separate equations. T is in all 3 of these equations. Solve for it in all 3 of the equations. And now I ask the much simpler question, under what circumstances is there a value of t that satisfies all 3 of these equations? And that's a freebie. When can there be a value of t equal to 3 different things? Those different things have to all be the same. Right? If there is a single value of t that is equal to 3 different things, I mean, if they're different, then there can't be a single value equal to all of them. Right? So, dumb example. Is there a value of t that equals 4 and 6 and 7? No, don't be ridiculous. Is there a value of t that equals 4 and 4 and 4? Why, yes, there is. It's 4. Right? So that's all that's going on here. So I just need to know that these 3 things are equal to each other. Notice that this is a point tester. You can give me any point x, y, z. I can plug in, compute these 3 things, and look, either these 3 things are all equal to each other or they're not. Simple as that. So this is what a point tester looks like for a line in space. It is called the symmetric equations for the parametric line. Very handy little trick. And we are out of time, so we'll draw the line right here for today and pick up here on, we have Monday off, right? So see y'all on Wednesday. Have a good one.